Hello everyone. So now today in this lecture we are going to discuss rotational vibration. So am I audible to everyone? Please confirm. Just one second. Yes. So today I am going to discuss rotational vibration of free undamped single degree of freedom system. And in this rotational vibration part, to solve the problem of rotational vibration, we will discuss two methods. One is equilibrium method. Some faculty also refer this as a torque method, and second is energy method. Okay, so why I have first of all chosen this topic now, because in single degree of freedom vibratory system now, most of the time student fails difficulty in calculating the natural frequency of rotational vibration system. That's why I have selected this topic. Okay, yes. So we are going to discuss two methods. One is equilibrium method and second one is energy method. So firstly, we'll discuss how to solve the problem of rotational vibration of free undamped single degree of freedom system by equilibrium method. Okay, for that I am taking an example. This example I have taken to discuss how to solve the problem by equilibrium method. First of all, what we will do now in this system now, you can see this is a rod. Try to understand the concept first now. This is the rod which is hinged at this location. Right now the mass of this rod is capital M. The mass of this rod is capital M. Okay, and which is hinged at this location. Okay, the length of the rod is capital L. Yes. Now in free end of this rod, one point mass is also attached, whose value is a small m. So this is point mass whose magnitude is small m. It is attached at the free end of the rod. Since it is attached at the free end of the rod, means can I say indirectly it is also the part of the rod because it is attached at the rod? Yes. Now what will happen? Now to support the weight of this rod at point mass, we attach two spring. Okay, you can see this is linear spring whose stiffness is K, and this is torsional spring whose stiffness is KT. Okay, so this is linear spring whose stiffness is K, and this is torsional spring whose stiffness is KT. Okay, now see how we can solve the problem by equilibrium method. Okay, see for that now, when we were solving the problem of spring mass system by simple spring mass system by equilibrium method, what was the method? To explain the concept, first I am taking this simple case. Just try to recall this case. This is a spring whose stiffness is K. Right now spring is massless na, and below this spring we have attached a point mass M. Right now it is translation system, but through this system I will explain this system also. Okay, now what will happen if we want to derive the equation of vibration for this case? Okay, this is general case, and whatever equation of vibration is coming for this case now, we'll remember that equation. Okay, but why I am explaining this now? Because to understand the concept of equilibrium method for this rotational vibration case, first you need to understand this. Okay, now what will happen? What is happening? Suppose I had displaced this mass from its mean position like this. After that I had released the mass, so definitely it will vibrate like this, and during that vibration I am taking any location which is displaced at a distance x from mean position. See, this is the mean position of this system. So I am taking a position in which this mass m is displaced from x distance from its mean position. See, here x is displacement from mean position. Definitely here, due to the weight of this mass, because weight will act in vertical direction, and due to that weight some static deflection will induce in the spring. But I am not talking about that deflection, because whatever static deflection will induce in the spring due to the weight of this mass. Okay, so due to that spring force will come. That spring force will be, suppose due to the weight of this mass, spring static deflection is spring is coming, which is delta. So spring force will be K delta. Just try to understand. Okay, I am talking about this mean position. At this mean position, weight is acting like this. Weight. Okay, don't write this. Try to understand only. So weight is acting like this. Yes. Now due to weight, suppose the static deflection of the spring is delta. So spring force will be K delta, and it will be opposite to the direction of deflection. Okay, so right now if due to this weight, spring will deflect in downward direction, so here this force will be in upward direction. Okay, now since it is static deflection now at mean position, right now I am not deriving the equation of vibration, I am talking about mean position. So at mean position net force will be 0, and if you will take net force equal to 0, this weight part will get cancelled with K delta. Okay, so what I am trying to say now, whenever we are deriving the equation of vibration, if in the direction of vibration due to weight, static deflection is coming in the spring. Then during deriving the equation of vibration, neither will consider weight nor will consider spring force due to static deflection. Reason? Because both force will eliminate each other. But how these two forces, right now I explained. Okay, but how these two forces are eliminating each other, we need not to bother about that, because right now this case was simple case. But if I'll talk this case again, you will do this analysis now. It has no sense, because ultimately if you consider weight, then we have to consider static deflection force also, and they will cancel each other. And if they are cancelling each other, what is the sense in considering those forces? So what I am trying to say, in the direction of vibration, if due to weight static deflection is coming in the spring, so these two forces will get cancelled with each other. So while deriving the equation of vibration, we will not consider these forces. Okay, that's why here this x is not total displacement of mass, it is the displacement from mean position. Okay, and if here we are not taking static deflection. If displacement from mean position is x, so right now you can see this spring is directly attached to the mass. So can I say displacement of spring will also be x? Okay. Now what is equilibrium method? First of all, here it is having translation motion. What is the meaning of translation motion? Right now the displacement of mass from mean position is x. So can I say its velocity will be x dot? What is x dot? It is the differentiation of x with respect to time. Similarly, its acceleration will be x double dot. What is x double dot? Again differentiate x dot with respect to time. So that will be acceleration. Okay. Okay. Now what about direction? See, whatever is the direction of x, right now we have taken x, it's below from mean position. Na? So x dot will also be vertically downward, x double dot will also be vertically downward. Why? Because we got x dot and x double dot by differentiation. Try to understand what I am trying to explain. Whatever is the direction of x na, if we are calculating x dot and x double dot by differentiation, the same will be the direction of x dot and x double dot also. Okay. I am not saying that acceleration can never be in this direction. It can be in this direction, but try to understand. If acceleration is in this direction na, automatically value of x double dot will come with minus sign. Okay. Suppose if actual acceleration is this side 5 meter per second square. So can I say na x double dot will be minus 5. And if I am using minus again, means its direction will be opposite to this. So if acceleration is upward now, automatically it will come with minus sign. If it is downward, automatically it will come with plus sign. Same is valid for x dot also. So whenever you are deriving the equation of vibration, first key point is whatever is the direction of x, same will be the direction of x dot and x double dot. Okay. Now what we'll do, we'll draw the FBD free body diagram of this mass. Here this spring is attached, so I'm cutting this. Okay. Now when you are drawing this free body diagram now, in this free body diagram, whatever force we'll consider, but before that, first try to analyze whether we need to consider weight or not. What is the concept now? Just try to understand in that system, due to weight or due to gravity, restoration will occur or not. If due to gravity, restoration is not occurring, restoration means when you will displace this mass from its mean position, it will try to come back to its mean position. The effect due to which this mass is trying to come back to its mean position, that is known as restoration. Okay. Definitely, since here spring is attached, so spring force will always be responsible for restoration. It is 100% sure. But what about gravity? So very simple. If in the direction of vibration, if either weight is not coming, here weight is coming, but suppose in some application in the direction of vibration, weight is not coming. In that case, there will be no role of gravity in the restoration. First case. Just listen these things, you need not to write. Second, if in the direction of vibration due to weight, static deflection is coming in the spring. What I am saying, due to weight, static deflection is coming in the spring, then weight and static deflection force will cancel each other, means again there will be no role of gravity in the vibration. So in such type of cases, we will not consider weight while deriving the equation of vibration, because it will cancel with static deflection part. And if we are not considering weight, means also not consider static deflection of the spring. And here x is not static deflection, it is the displacement of from mean position. Okay. So here, since in the direction of vibration you can visualize due to weight, static deflection will come in the spring, they will cancel each other. So here there will be no role of gravity in the restoration. You can in separately you can write like this, there will be no role of gravity in the restoration. So while deriving the equation of vibration, neither will consider weight nor will consider static deflection part. They will cancel each other, but how they are cancelling, we need not to bother about that. So apart from that, now what will force will come? One force is spring force, but which is spring force? Due to this displacement. Don't bother about the displacement of mean position. Okay. So right now, how to calculate spring force due to linear spring? Stiffness of the spring is K. Now, if displacement of mass from mean position is X, so here displacement of spring is also X. So here spring force will be Kx. It will be opposite to X. Right now, X is downward, so it will be upward. And this force is nothing but restoring force. And you can see, if you are displacing this downward, this force will try to move this mass in upward direction. Means it is trying to move mass towards mean position. That's why it is restoring force. So here restoration is occurring due to stiffness. Okay. So one is restoration. Second is here, since this mass is having acceleration now, so here one more force will come into picture, that is inertia force. And when you are deriving an equation, if you are considering inertia force, in that, after considering inertia force, can I say we can use D'Alembert principle, which says that if you are involving inertia force in any body, then after involving inertia force, net force in the system will be zero. This is the D'Alembert principle. Okay. And how we can draw inertia force? So see, inertia force will come for that body whose inertia is there. So here inertia of mass or mass of is m. This is mass m. It is having linear motion whose velocity displacement is x, velocity is x dot, acceleration is x double dot. So inertia force will always be m for linear motion, m into x double dot, which is acceleration. And its direction will always be opposite to x double dot. Right now x double dot is downward, so it will be upward. Okay. And after involving inertia force, net force in this system will be zero. So right now all forces are coming in vertical direction. So I am taking summation of force in vertical or y direction equal to 0. Now just use equation. Suppose this, while using this summation, I am adding upward and subtracting downward. So mx double dot is upward, so plus sign, kx is upward, so plus sign, that is equal to 0. So this is the equation of free undamped vibration of general case. General case means when spring is directly attached to the point mass like this. Okay, you can remember this equation. Okay, yes. Okay, now I am not going to solve this equation because right now I am not explaining differential equation, but this is the equation of general case of free undamped vibration. Okay, mx double dot plus kx equal to 0. But how I had derived this equation? I had draw the FBD of this displaced position, in which I involve two type of forces. One is restoring force, one is inertial force. Okay, restoring force and inertial force. And after involving inertial force, we can say net forces and movement in the system will be 0. Right now it is having translation motion, so I am using net force in y direction equal to 0. We got this equation. Now, whenever the equation of vibration is coming like this now, from this equation, now you can calculate the natural undamped frequency of this space system, which I am denoting as omega n. For general case, I think you have remembered the formula also. Formula to calculate omega n is root k by m. Okay, but mathematically, this omega n is nothing but natural frequency of this system, root k by m in radian per second. Okay, but what is k na? As per this equation, it is the coefficient of x. What is m? It is the coefficient of x double dot. And if you know the coefficient of x and x double dot, you can calculate omega n, which is nothing but root over k by m. And after calculating natural frequency in radian per second, you can calculate frequency in hertz also, because formula to calculate frequency in hertz is 2 pi by omega n. You can calculate time period of vibration also, of natural vibration also, which is omega n upon 2 pi. Okay, but for that, first we need to calculate omega n. But that was having linear vibration. Now we'll apply same concept in this case, where rotational vibration is occurring. Now, what is the method? Now, method is same. Only difference is it is rotating. Now, if it is vibrating by rotating, now like if you rotate this rod, and if this rod is rotating, this point mass is also rotated because it is attached to the rod. About this point, suppose I rotated by in clockwise direction like this. After that, I release the rod, so it will vibrate like this. And when it will vibrate, it is vibrating through rotation. That's why it is rotational case. Okay. So in that case, what we'll do now? First, we'll locate the eye center of this rod. Suppose if I am drawing the FBD of this rod, in this point mass is also attached the rod in the rod. So if I am drawing the FBD of rod, means I am drawing the FBD of this point mass also. Okay. So since this rod is hinged at this location, so can I say this is the point about which this rod is rotating? Now see, the point about which any rod, any link is rotating now, that point is known as eye center. What is eye center? Very simple. I center is the point about which you can assume at an instant any body is rotating. Like here, this rod will always rotate about this point. So this point is nothing but it is I center. I center. Okay. Now see, point mass is also attached to the rod. So if rod is rotating about this point, which is I center of the rod, so can I say point mass will also rotate about this point? So it is the I center of point mass also. Okay. Now why I am explaining this? See, whenever any system is having rotational vibration, I will solve the as per numerical, but first I am explaining the concept. So see, in linear motion, translation vibration, what I am doing? After involving inertial force, I was using summation of force in the direction of vibration is 0. This I was using in translation vibration. Yes. Similarly, when it is having rotational vibration, can I say summation of moment about any point? Summation of moment about any point will be 0 after involving inertial forces or inertial force movement, whatever is coming here. I will explain how to calculate inertial force or inertial movement. Okay. But when I'm saying it is 0 now, it is 0. I will use this in case of rotational vibration. Rotational vibration. Okay. But this equation I can use after involving inertial forces or movement. And how we can calculate this inertial force and movement, I will explain, don't worry. Okay. Now here now you can take movement about any point, but your question solving approach will become easy if you are taking movement about I center. If you are taking movement about I center. So whenever I will use this equation, now I will take movement about I center. And what I am saying, in rotational vibration, after involving inertial force or movement, we can say summation of movement about I center will always be 0. Okay. So here take always movement about I center. And which point is known as I center? I center is the point about which any link is rotating during vibration. And right now, whether this rod you are talking, whether you are taking this point mass, because point mass is also attached the rod, it is rotating about this point. So in this case, this is the location of I center. Okay. And after involving inertial force or movement, you can use summation of movement about I center equal to 0. Okay. Okay. Now how we can derive the equation? So for this question I am deriving now. See, this is the I center now. Yes. First of all, what we'll do now, we'll rotate this rod about I center. So take any position in which this rod has rotated about I center by theta angle from its mean position. Okay, you can take theta clockwise also, you can take theta anti-clockwise also, your will. So right now I am taking theta clockwise. So suppose I am taking any position in which this rod has rotated by theta angle from its mean position. This is the displacement from mean position. Again, we need not to bother about mean position, because again you can see in this diagram, due to the weight, here vibration is occurring like this, and due to the weight, whether we are taking the weight of rod, whether you are taking the weight of point mass, can I say due to weight, static deflection will induce in the spring? Because if there are no spring, this rod cannot be like this, it will take this position. So why this rod is in horizontal position? Because they are supported by spring. So what will happen? Due to this weight, there will be static deflection in the spring, and weight and static deflection will cancel each other. And if they are cancelling each other, so while deriving the equation of vibration, will not consider weight, because here there is no role of gravity in restoration, because weight is getting cancelled with static deflection. And we are not considering weight now, will also not consider the static deflection of spring. So here this theta is not displacement of mean position, it is displacement from mean position, because neither we need to bother about weight, nor we need to consider the static deflection of the spring due to weight. Okay, so it is the displacement from mean position. Okay, and here there is no role of gravity in the restoration. This is first conclusion. Now in this mean position will apply all the forces and or movement. When I am saying forces, means I am talking about both forces and movement. And mainly we have to consider two type of forces or movement. I am not saying two force will come. I am saying two type of forces and movement. One is restoration and second is inertia. So first I am explaining how to calculate inertial forces and movement, that you already know, but here I am explaining. So see, here first I am explaining how to calculate restoration force and movement. So see, here restoration is occurring due to stiffness, and due to stiffness, calculation of restoring force or movement is very easy. First only see, the spring which is attached in the system is linear spring or torsion spring, right? Like here it is linear spring and here it is torsion spring. Due to linear spring, restoring force will come. And what is the method to calculate restoring force? This linear spring is attached here, its stiffness is K. Now see, what is the displacement of this linear spring from mean position? This is the displacement. Suppose this I am denoting as x1. Okay, I am drawing the abidine. I have cutted the spring from this location and I am drawing the abidine of this rod. Okay, so inertial force will be K into displacement of spring from mean position is x1. So inertial force will be Kx1 first of all. Sorry, I am saying inertial force, it's my bad. It's a restoring force. Due to stiffness, restoring force will come. Na? So restoring force will be Kx1. Its direction will always be opposite to x1. Right now x1 is downward. It is very easy. Just I am explaining. That's why I am taking the time. So it will be, if we are drawing the abidine of rod, it will always be opposite to displacement. Right now x1 is downward, so it will be upward. Yes, this is restoring force due to this spring. Now one more spring is attached there. This spring, but it is torsional spring. Now, like due to linear spring, restoring force is coming now. Due to torsion movement, spring, restoring movement will come because it resists movement. What is the method? Restoring force is K, if stiffness is K, displacement is x1, restoring force is Kx1. Similarly, in restoring movement, instead of K, KT will come. KT is nothing but torsional stiffness of this torsion spring, and it is given already. And instead of linear displacement, angular displacement will come into picture. Means instead of x or x1, theta will come. So right now you can see that stiffness of this torsion spring is KT. So here restoring moment will come, which is KT into its angular displacement from mean position. So this rod has rotated by theta angle from mean position. So this spring will also displace by theta angle from mean position. So restoring moment will be KT theta. This is the value. Now direction, it will be opposite to theta in the abidine of rod. Right now theta is clockwise, so it will be anti-clockwise. Clear? Now no other spring is attached, so we have completed the restoring part. Why I am not considering the weight? Reason, because there is no role of gravity in the restoration. Reason, because due to weight, static deflection is coming in the spring, which are cancelling each other. Okay, if you want, you can remember this also. Whenever any horizontal rod is hinged at any location and their weight is supported by spring, there will be no role of gravity in restoration. So during the derivation of vibration, you need not to consider the weight. And if you are not considering the weight, also not consider static deflection. Okay. Now, but we have to calculate, consider inertial forces or moments. So see, what about inertial force? I am discussing separately. Whenever inertial force or moment, whenever any body whose mass is m is translating for translating body. Okay. In translating body, inertial force will come into picture. Like here we have taken. And inertial force will be, suppose mass of that translating body is m, it is displacing from mean position is x, so velocity will be x dot, acceleration will be x double dot, and inertial force, for inertial force I am using Fi, it will be mx double dot. Okay, and its direction will be opposite to x double dot, like x double dot is downward, so it will be upward. Very simple. But see, if any body is having rotational motion or rotational plus translation motion, okay, that case I will also take later. Rotational or rotational plus translation motion. Method to solve the problem of both cases are same. In that case, what we will do first find the I center of the system. Like here, I center of the system is this. Okay. Now here in this case, instead of inertial force, inertial moment will come. With that I am denoting as Mi. And it will be equal to I about I center. What is this I am explaining? Into angular acceleration. Angular acceleration means, suppose the rod whose inner mass inertia is I, angular displacement of rod is theta. So angular velocity will be theta dot, angular acceleration will be theta double dot. So inertial moment will be I about I into theta double dot. What is I about I here? It is the mass moment of inertia of the rod or link, whatever it is, mass inertia of the inertial body, whose inertial moment I am taking, body, about I center. And you should know how to calculate mass inertia about any point. Okay, whichever numerical I am taking, in that numerical I will explain what is the method to calculate mass inertia of that question. Okay, but right now in today's class I am not focusing in explaining the calculation of this. This you should know. If you this calculation you are knowing, then how we can derive the equation of this case, that I am explaining. Okay. So what is I about I? It is mass inertia of the inertial body about I center. And if theta is angular displacement, theta double dot will be angular acceleration, and it will be opposite to theta double dot. Like if theta is clockwise, theta dot is also clockwise, theta double dot is also clockwise. So for this type of case, it will be anti. So whenever any system is rotating now, first calculate I about I center of this system, then inertial moment will be I about I into theta double dot. Very simple, very simple. Yes. So right now inertia of rod is also given and inertia of point mass is also given. But can I say for here two type of inertial bodies coming? Suppose this is body 1, this is body 2. But can I say I center of both body is this point I? So first calculate the mass moment of inertia of both the body about this point. So first I am calculating mass inertia of body 1 about this point, that is rod. Then I am calculating mass inertia of point mass about this point. Okay, then add them, we will get total mass inertia about I center, because for inertial moment we require I about I. Yes. Now for this question I will calculate, but see, if you know the mass inertia of any body about its center of gravity, like suppose this is the rod, I am taking the diagram of rod, you can remember this formula. This I am explaining separately. The mass of the rod is suppose capital M and length of the rod is capital M. Then for this rod, the formula to calculate mass moment inertia about its center of gravity, and for rod center of gravity will come at the middle, is ml square by 12. First of all, we will remember this formula. Okay, for rod you have to remember this formula. The formula to calculate mass inertia of this rod about center of gravity is ml square by 12. But this is about center of gravity. But if suppose my objective is to calculate mass inertia about this point, suppose this point is A. So if I want to calculate mass inertia about A, how I can calculate? So see, if you know the mass inertia of this body about center of gravity now, then by using a theorem which is known as parallel axis theorem, I can calculate mass inertia of this body about A also. How? See, I am writing the formula. See, suppose I want to calculate mass inertia of this body about A. The formula to calculate this will be, this is equal to, first of all, calculate mass inertia of that body about their center of gravity, which is G. So first calculate I about G, which is for rod it is ml square by 12, plus mass of this body, which is M, into r dash square. Now what is r dash here? It is the distance between this center of gravity and the point about which we are calculating I, means point A. Okay, and do the square of this. Okay, so this is the formula to calculate mass inertia about other point if you know the mass inertia about center of gravity. Okay, and for rod, the formula to calculate mass inertia about center of gravity is ml square by 12. Yes. Now, similarly for a point mass, so see, for point mass, the formula is very simple. Suppose this is point mass, which is small m. Okay. Point mass means the mass of this point mass is concentrated at a single point, and this is also the center of gravity of point mass. Now, suppose I want to calculate mass inertia about point A, and this distance is r dash. Okay. See, first of all, now you can directly remember the mass inertia of point mass about center of gravity will always be 0. Okay. Reason, because point mass is concentrated at one point, and that point is also center of gravity. So since point mass is concentrated at one point, which is at center of gravity, so its mass inertia about center of gravity will always be 0. Okay. But it is about center of gravity. But if you want to calculate about A, again use parallel theorem. But for point mass, you can directly remember the formula. What is the about A? So this will be equal to, first of all, point mass, use this same formula. So mass inertia of point mass about center of gravity, which is 0, plus mass of this point mass M, into distance between this point and point A, which is r dash. So r dash whole square. Na? So it will come m r dash square. So for point mass, you can remember, if you want to calculate mass inertia of point mass about any other point, simply use mr square formula, where m is the point value of point mass and r, here I am representing as r dash, that is the distance between that point mass and the point about which you want to calculate I. Very simple. So you understood this calculation. So now I am calculating the mass inertia of this rod and point mass about I center. I am calculating one by one. First I am calculating for rod. So what we will do? First calculate mass inertia of rod about the center of gravity of rod. Okay. The center of gravity of the rod will be at middle. Suppose this distance is L by 2. This is center of gravity of rod, that is G1. And now, so to calculate mass inertia of rod about I center, I need to use Paris theorem because I center is not coinciding with G1. So first calculate about G1, and we know the formula to calculate mass inertia of rod about its center of gravity is ml square by 12. So here mass of rod is capital M, Length is capital L square divided by 12. But it is about center of gravity. Now to calculate about I center, we'll use extra theorem. So in this add plus mass of this rod, which is capital M, into r dash square, where r dash is distance between center of gravity of rod, that is G1, and I center. And right now this distance is L by 2. So it will be L by 2 whole square. Yes. So this is mass unit of rod 1 about I center. This I am representing as I1. For rod I am using 1 na. So now simplification is your part. ML square you can take common. It is 1 by 12 plus L square. ML square I have taken common. 2 to 4. 1 by 4. This is 3 by 4 plus 1 by 4. 4 by 3 by 12 plus 1 by 12. 4 by 12. 4 by 12 is 1 by 3. So it is coming ML square by 3. You can check calculation. So this is mass units of the rod about I center. Now what about point mass? So for point mass, whatever mass unit is coming about I center, I am representing as I2. It will be, for point mass formula is very simple. Mr square, M is the value of this point mass, which is small m, into R is the distance between this point mass and the point about which we are calculating I. And right now I am calculating I about I center. So distance between I and this point mass, which is equal to length of the rod L. So it will be Mr square. So now I can calculate total I about I by combining the inertia of rod and point mass. So it will be mass units of rod about I center is capital ML square by 3 plus for point mass it is ML square by 3. So in I about I included the inertia of both rod and point mass. So now we can apply inertial moment over here also. Inertial moment will be I about I center into angular displacement of the rod is theta. So angular displacement of point mass is also theta. Then if angular displacement theta, right now you can see theta is clockwise. So theta angular velocity will be theta dot clockwise, angular acceleration will be theta double dot clockwise. So inertial moment will be I about I into theta double dot. And I have taken the inertial moment of both rod and point mass, because in I about I am taking the mass unit of rod also and point mass also. And it will be opposite to theta double dot. Theta double dot is clockwise, so it will be anti-clockwise. Very simple. Clear? So I have applied restoration, I have applied inertia. So after that, can I say this will be in this net force and moment will be 0. So what I am taking? I am taking summation of moment about I center equal to 0. And while using this equation, it is your will. If you want to add clockwise, then subtract anti-clockwise. If you want to add anti-clockwise moment, subtract clockwise. Okay. Now you can tell, sir, here it is hinged. So at hinge support reaction should also come into picture. Yes, it is true. But see, if I am taking moment about I center, which is hinge point here also, so the moment of reaction at hinge, because at hinge support always force reaction will come. And formula to calculate moment due to force is force into perpendicular distance. And perpendicular distance of these forces from I center is 0. So their moment about I center will be 0. So here we need not to bother about the reaction which is coming at hinge, because their moment about hinge will be 0. Okay. So that's why I'm not considering the reaction here, because their moment about hinge will be 0. Now one by one. First I am taking inertial moment part. So already it is moment. So it will come as it is now. I about I theta double dot. It is already moment. So here will not multiply distance. If you are calculating moment due to force, then moment will be force into perpendicular distance. But here already it is moment. Direction is anti-clockwise. Whatever first direction is coming now, right, it is anti-clockwise. I am taking that direction as positive. So anti-clockwise plus opposite to this, that is clockwise, will be minus. So right now it is anti-clockwise. I about I theta double dot. Now restoration part. This is restoring moment kt theta, already a moment. Anti-clockwise, for anti-clockwise I am taking plus sign, so plus kt theta. Now to do this, this is force, and moment due to force will be force into perpendicular distance. So force is kx1. Now it's perpendicular distance from I. So it is vertical, so it's perpendicular means horizontal distance from I, which is a. So moment due to this force about I is kx1a. Now how it is rotating about I? This force is like this. You can see about I, it is rotating anti-clockwise, and right now for anti-clockwise I am using plus sign. That's why plus sign. Yes. No other forces are coming. So completed. Moment of reaction at I about I will be 0. So we need not to bother about that reaction. So this is summation of moment about I, which is equal to 0. But here x1 is coming now. So I will also write x1 is a displacement. So in terms of angular displacement, I will write the expression, find the expression of x1 in terms of theta. Okay. So how we can find? So see, this is the x1, is the displacement of this point. And can I say for small oscillation, whenever we are deriving the equation of vibration, it is based on the assumption that oscillation is small, means this displacement is less. For a small displacement, if you want to calculate x1 in terms of theta, just see the distance of this point from I center. if distance of this point from eye center is a na, nearly this x1 will be a theta. Actually, if you use proper mathematics na, it will be a sine theta, because after displacement this distance will be a. So it will be a sine theta, but for small oscillations sine theta and tan theta is nearly theta. So I am deriving the equation of vibration for small oscillation. So you can directly write x1. Just see the distance of this point from eye center, it is a, and angular displacement theta. So x1 will be a theta. So I'm replacing x1 by a theta, and I about I we know it is capital ml square by 3 plus small ml square theta double dot plus kt theta plus k x1 is a theta. Okay, or already this a is coming to 0. Now you can see this equation of vibration is coming in standard form. Standard form is ml square by 3 plus small ml square theta double dot plus, here I can take theta common, so it will be kt plus ka square theta equal to 0. You can see that mathematically na, this equation and this equation is nearly same. Here mx double dot plus kx, here displacement is coming x, so here double differentiation of x with respect to time is coming. Here you can see, here angular displacement theta is coming, so here double differentiation of theta with respect to time, that is theta double dot is coming. So both equations are mathematically same. So in this case, you can easily write the equation of omega n. For that, what we'll do now, in this standard equation, when I'm saying omega n, it is natural frequency of the system in radian per second. Radian per second. Okay. So just consider the coefficient of theta as ke. Okay, like in general case it was k. Now for other case, we'll consider this as ke. Similarly, the coefficient of theta double dot as me. Me is not a mass. It is just the coefficient of theta double dot. Yes. Then formula to calculate omega n is nothing but it is square root of ke by me, where k is the coefficient of theta and me is the coefficient of double dot. It doesn't necessarily here always theta should come. Here if x is coming, here x double dot should come. Here if x1 is coming, here x1 double dot should come. Here if phi is coming, here phi double dot should come. Then the coefficient of displacement is ke, coefficient of double differentiation of displacement with respect to time is me. Then omega n will be root over k by me. Like in this case, as per this expression, k is kt plus k square upon me is capital ml square by 3 plus small ml square. Completed. This is natural frequency radian per second. After that, you can calculate frequency in hertz also, which will be omega n upon 2 pi. You can calculate time period of natural vibration also, which is 2 pi by omega n. So like this, by equilibrium method, you can solve the problem of rotational vibration. But right now I had taken that case in which there was no role of gravity in the restoration. I am discussing based on this concept one or more two question. After that, I will explain that case also in which gravity will also play important role in restoration. But before that, based on this concept, I am discussing one more question. Just see, this is with me you can also practice this question. See, this is multiple choice question. What this question is saying, this is very good question. A thin uniform rod of rigid of length capital L, the rod of length of this rod is capital L, and mass capital M is hinged at O. It is hinged at this location. Okay. Yes. From this point, its distance is L by 3. Total is to L. It is L by 3. So definitely this distance will be L minus L by 3. That is 2L by 3. Good. Now, the bar is further supported by a spring, each of its stiffness scale located at the two ends. It is shown in figure. They are linear spring. A particle means point mass, of mass small m, but small m is given in terms of capital M. Small m is capital M by 4. So this is, don't get it is the error in making the diagram. The mass of the rod is capital M, and the mass of this particle is small m, which is capital M by 4. It is given in the question. Small m is capital M by 4. It is fixed at one end of the bar as shown in figure. This diagram is given. Now for small rotation, means again I am rotating this rod in a small amount, then releasing this. So what will be the natural frequency of the system? Now whenever examiner asking natural frequency, but unit is not mentioned. Now here examiner has not mentioned whether we have to calculate in radian per second or hertz. So always first calculate in radian per second. If radian per second option is present in the, whatever answer is coming in radian per second, if that is present in the option, means just think examiner asking radian per second and tick that. But if that option is not present, then assume examiner asking in hertz. So then calculate frequency in hertz, which will be omega n upon 2 pi. Okay. And if frequency in radian per second is not mentioned in the option, it is 100% sure examiner will mention frequency in hertz in the option, because incorrect question cannot come in exam, na? Okay. So either examiner will ask in radian per second or in hertz. So only one option will be there. So first calculate in radian per second, omega n. If that is in the option, tick that. If not that in the option, then calculate frequency in hertz. If radian per second frequency is not in the option, I am 100% sure frequency in hertz will be in the option. Okay, but just first I am calculating omega and that is frequency in radian per second. For that, again see, it will have rotational vibration, and you can see this rod is hinged at this location. So can I say this point O is nothing but the eye center of the rod, because rod will always rotate about hinge point. Okay. Now this point mass is also attached at the rod. So if rod is rotating about O, which is eye center of the rod, so point mass will also attach rotate about O. So can I say point I is, that is point O is also the eye center of point mass also. So here point mass of both rod and point mass is I. So what I am doing, first I am calculating mass moment ratio of the rod. Suppose for rod I am using suffix 1, and point mass, for point mass I am using 2, about eye center, because their eye center are same. So first I am calculating mass moment ratio of rod about eye center. That I am representing as I1. I will calculate. First calculate mass moment ratio of the rod about center of gravity. If that is not coinciding with eye center, then use Parakram's theorem. So first locate the center of gravity of rod. Center of gravity of the rod will be at middle. Middle means from this point it will be at a distance L by 2. L by 2 is more than L by 3. So it will be somewhere here. This is the center of gravity of rod. And see, this distance is L by 2. Okay. Now if it is L by 2, what about this distance? It will be L by 2 minus L by 3. And we'll do calculation. L by 2 minus L by 3. LCM is 6. 2 3 is 6, so 3L minus 3 2 is 6, 2L. So it is L by 6. Calculation is your part. Now I'm not going on too much in calculation. Yes. So this distance is L by 6. So what about I mass units of rod about eye center? I1, that will be mass is rod about the center of gravity of rod, that is G1. It will be ml square by 12. M is the mass of rod, which is capital M, into L is the length of the rod, which is capital L square, divided by 12. Now it is about center of gravity, that is about G1. Now to calculate about eye center, we'll use Parakram's theorem. So for that, what we'll do in this, add mass of the rod capital M into R dash square. And what is R dash? The distance of center of gravity of rod, that is G1, and eye center. And this distance is L by 6. So it will be L by 6 whole square. Calculation in your part, it will be ml square, I take in common. Okay. So it will be 1 by 12 plus 1 by 36. 12 3 is 36. So 3 by 36 plus 1 by 36, 4 by 36. 4 by 36 is 1 by 9. Nah? It will be ml square by 9. Calculation is your part. So this is mass units of rod about eye center. Now what about point mass? So for point mass, mass units of point mass about eye center, I am representing I2. It is very simple. Formula to calculate point mass units of any point mass about any point is mr square, where m is the mass of that point mass. Right now mass of this point mass is small m, but we know small m in terms of capital M. First I am writing in terms of small m into r square. What is r? R is the distance of this point mass and the point about which we are calculating I. And we are calculating I about eye center. So this distance, which is 2L by 3. So into 2L by 3 whole square. Very simple. Okay. Now small m is capital M by 4. Why I am calculating in terms of capital M now? Because examiner has given all the option in terms of capital M. Okay. So small m is capital M by 4. 2L by 3 whole square will be 4 by 9 L square. 4 will get cancelled. So it is coming ml square by 9. So after that I can calculate total. Total means by combining the inertia of rod and point mass, we can calculate total mass inertia about eye center. And it will be mass inertia of rod about eye center, which is capital ml square by 9, plus mass inertia of point mass about eye center, which is again capital ml square by 9. So total mass inertia about eye center is coming 2 by 9 capital ml square. Clear? Now I can derive the equation of vibration, and again I am using equilibrium method. For that, not take any position during vibration in which this rod has rotated by theta angle from its mean position. But before that, first decide whether there will be role of gravity in the restoration or not. So again here there will be no role of gravity. You can remember also, whenever any horizontal rod is hinged at any location and their weight is supported by spring, there will be no role of gravity in restoration. The reason? Because due to the weight of the system are supported by spring. So due to weight, there will be static deflection in the spring, and they will cancel or counter the effect, their effect. So that's why neither will consider weight nor will consider static deflection part during the equation or during the equation vibration. So here I am writing there is no role of gravity in the restoration. Now see. So take any position in which this rod has rotated by theta angle from its moon position, and right now I am taking theta clockwise. So after rotation, this diagram will be like this, and this angle is theta. Right now write again theta clockwise. So theta dot will also be clockwise, theta double dot is also clockwise. Now here spring is coming, so I am calculating displacement of this point. Suppose displacement of this point is x1. What will be the expression of x1 in terms of theta? It will be x1. Now distance of this point from eye center is 2l by 3. So can I say x1 will be 2l by 3 theta? Yes. Similarly, here also spring is coming now. So what about displacement of this point? Suppose this I am representing as x2. It will be x2 is displacement of this point. Now distance of this point from eye center is l by 3. So can I say x2 will be l by 3 theta? Okay. So now I am involving all the forces and movement, and we have to involve mainly two type of forces and movement. One is restoring and second is inertial. So first of all, restoring. So here restoration is occurring due to stiffness. So we'll consider restoring force of movement due to stiffness of spring. And right now it is linear spring, so restoring force will come due to this spring. Stiffness of this spring is K. Its displacement from mean position is x2. So restoring force will be kx2. Now what about direction? If you are drawing the FBD of rod, direction of this restoring force will be opposite to x2. Right now x2 is upward, so it will be downward. Now restoring force due to this spring. So stiffness of this spring is K. Displacement from mean position is x1. So restoring force will be kx1. Now direction, it will be opposite to x1. Right now x1 is downward, so it will be upward. No other spring is coming. Okay. And since there is no role of gravity in restoration, so I am not considering the weight. Now what about inertial? So right now this rod and point mass is rotating about eye center. So we'll take inertial moment. And formula to calculate inertial moment is I about eye center into theta double dot means into angular acceleration. Okay. So right now by combining the inertia of rod and point mass, total I about eye center is II, whose expression is 2 by 9 ml square. So inertial moment will be I about eye center, which is 2 by 9 capital ml square, into angular displacement is theta, so angular acceleration will be theta double dot, so into theta double dot. Now direction opposite to theta double dot. Right now theta double dot is clockwise, so it will be anti-clockwise, and apply at eye center. That's it. Okay. And this is total inertial moment now, because in I about I consider the inertia of rod also and inertia of point mass. That's it. No other force will come. So in this ability, now what we'll do, we'll take summation of moment about eye center and equate with 0. And while using this equation, you need not to bother about the reaction which is coming at eye center region, because the moment of reaction at hinge or eye center about eye will be 0. So don't bother about the reaction which is coming at eye center. Okay. Now one by one. First I am taking this inertial moment I about eye theta double dot. It is already a moment, so it will come as it is. Now its direction, it is anti-clockwise. Suppose whatever first direction of moment is coming, I am taking that as positive. So for anti-clockwise I am using plus sign. So then for clockwise use minus sign. Now moment due to this about eye center, it is force, and formula to calculate moment due to force is force into perpendicular distance. This force is kx1. Now its perpendicular distance from eye center is vertical, so horizontal distance from eye center, which is 2l by 3. Now what about direction? So see how this force is rotating about eye center. This force is like this. About eye center it is rotating anti-clockwise, you can check. And for anti-clockwise I am using plus sign. So here plus will come. Clear? Very simple. Now moment due to this force about eye center, so this force is kx2. Its moment about eye center, so you this force, for that find the perpendicular distance of this force from eye center. It is vertical, so horizontal distance, it is l by 3. Now how it is rotating about eye center? So it is like this. About eye center it is rotating anti-clockwise, and for anti-clockwise I am using plus sign, so that's why plus. That's it. Okay, moment of reaction at eye center about eye center will be 0, so don't bother about the reaction which is coming at eye. So this is completed. Now this is equal to 0. Now just put the values now. I about I is 2 by 9 capital ml square theta double dot plus k. See, x1 is, now I am directly writing, x1 is, you can see 2l by 3 theta. So ultimately 2l by 3 theta into TL by 3. So it will be 4 by 9 L square theta. So can I write like this now? It is 4 by 9 L square and K is already coming. So 4 by 9 KL square theta plus. Similarly, value of x1 is L by 3 theta. You can check. Now L by 3 theta into L by 3, it will be L square by 9 and K is already coming. So it will be KL square by 9 theta equal to 0. So ultimately it will be, it is 2 by 9 ML square theta double dot plus 4 by 9 plus 1 by 9 is 5 by 9 KL square theta equal to 0. It is in general form. Now if we are considering theta, coefficient of theta is Ke, then it will be Me, omega n will be root over Ke by Me. Or if any term is coming common na, because common part will come this side, it will, if you shift this side, it will become 0 because RH is 0. So little bit calculation will be easy. So, yeah, like you can see in both the part na, L square by 9 part is common. So I'm taking common part outside, it will come this side, it will become 0. And after taking L square by 9 common, here 2m is remaining. So 2m theta double dot plus 5k theta equal to 0. So a little bit calculation will be. Again, it is in general form. Now for this, consider the coefficient of theta as Ke, which is 5k, double dot as Me, which is 2 capital M. Then omega n will be root over Ke by Me. As per this equation, Ke is 5k and Me is 2 capital M. So omega n is root over 5k by 2 capital M. Even if you are considering this as Ke and this as Me na, and you will calculate omega n, finally you will get same answer. Whether you are taking common or not, answer will not change. But just for easy calculation, I had taken L square by 9 common. So ultimately, omega n is coming root 5k by 2 capital M. So natural undamped frequency of this system in radian per second is root over 5k by 2 capital M. It is in radian. Now see whether this value is mentioned in the option or not. If it is mentioned, this will be correct answer. Root over 5k by 2 capital M. Yes, it is mentioned. In which option? Option B. So for this question, the correct answer is B for Bombay. So this is all about equilibrium method. But right now I have taken those questions in which there was no role of gravity in the restoration. Now I am taking that question in which gravity will play important role in restoration. Again, calculation is simple. I will discuss two questions from this concept. See what this question is saying. A massless rod of length L, the length of the rod is L, it is massless, is hinged at top point. Good. And a point mass M is attached at bottom. Okay, so this point mass is small m. Now rod is slightly rotated about top because it is hinged at top, then released. So it will vibrate like this, and we have to calculate the time period of that natural vibration. Okay. Now see why it will vibrate. Here spring is not attached. Then also it will vibrate because here restoration will occur due to gravity. Reason. Okay. Here na mass will vibrate like this. Okay. So what will happen now? What will happen? Suppose you have rotated this rod about I center. Now just don't draw this. Try to understand by theta angle. Okay. After that, it will release this. Now this you can feel this. This rod will try to come back to its mean position. Reason, here spring force is not coming. But even if spring force is coming now, whatever concept I am explaining here, that will always play its role in restoration. What will happen now? Here weight of the mass, point mass will be like this. But you can feel the one component of weight will come in this direction. One component will be in this direction but focused in this component. And can I say due to this component, it will try to come back to its mean position? Yes. Means here restoration is playing important role. Sorry, gravity is playing important role in restoration. And here since restoration is occurring due to gravity, here I am writing G, and in G I am taking tick mark. Tick mark means here restoration is also occurring due to gravity. So in this such type of cases, whenever you will derive the equation of vibration, now we cannot ignore weight, because here weight is not cancelling due to with static deflection, because here weight is playing important role in restoration. Even if spring is attached, suppose in this diagram examiner want to take your concept, so it might also examiner attaching spring also. If spring is also attached, so definitely restoration will occur due to stiffness also. But it doesn't mean here restoration will not occur due to gravity. Where there is spring is present or not, here restoration will occur due to gravity. But okay, and this you can understand by feeling. Feeling means even now whether spring is attached or not. Okay, at mean position this rod will always be like this. Okay, rod is in mean position like this, not due to spring. Whether there is spring or not present spring, in mean position rod will always be like this. And after that it will disturb this from its mean position, even spring is not present, it will try to come back to its mean position. And even without the presence of a spring, if it is trying to come back to its mean position, reason is very simple. It is coming due to gravity. So here gravity will play an important role in restoration. And how? Okay, for rod you can remember, whenever vertical rod is hinged at any location like this, whether a spring is present in the system or not, there will be role of gravity or weight in the restoration. Okay, and when we'll derive the equation of vibration, we'll consider weight also. Okay, weight also. Okay, simply now just see at the mean position due to weight in spring. If spring is present, right now spring is not present, but if it is present, just think whether static deflection will present in the spring or not. Here, if I will attach spring also now, then also due to weight there will be no static deflection in the spring, because weight of this system is not supported by this spring. So here weight will not cancel with static deflection part. So here weight can come in the picture in the equation of vibration, because it is not getting cancelling. So in this type of case, when we'll derive the equation of vibration, we'll consider weight also, that is gravity force also. Okay, so here right now I am considering, very simple. Okay. Now again, first locate the eye center, because it is rotating. So this rod is attached in this location. So can I say this point is the eye center of the rod? Yes, but it is the eye center of rod. But point mass is also attached to the rod. So ultimately point mass is also the part of rod, na? So it is the eye center of point mass also. And before proceeding further, I am calculating I about eye center. Okay. Now I about eye center, I have to only calculate about point mass. Reason? Because rod is massless. And for point mass, formula to calculate mass unit about any point is mr square. So m is the mass of point mass, which is small m. And what is r? R is the distance of this point at eye center, which is equal to L in this case, ml square. Now I am taking any position during vibration in which this rod has rotated by theta angle from its mean position. And right now suppose I am taking theta in anti-clockwise direction. So after rotation, diagram will be like this. And point mass will come here. And the center of gravity of point mass will be this point. Na? This length is X, and this angle is theta. Now see, right I have taken theta anti-clockwise. So theta dot is also anti-clockwise, theta double dot is also anti-clockwise. Now, first of all, in restoration, which force will consider? Since here restoration is occurring due to gravity, we'll consider weight. And we know weight is very simple. Weight is always m into g. Its direction will always be vertical downward, and it will act at the center of gravity. Right now, weight, inertia of only point mass is given. So inertia, weight of this point mass will be, why I am considering weight? Because here restoration is occurring due to gravity. Very simple. So mass of point mass is small m. So weight will be small mg. It will be vertical downward, and it will act at the center of gravity, and center of gravity of point mass is this point. So it will come here. I am drawing the ability of this displaced position. So draw forces in this displaced position. So this is weight. No other inertia is given, so restoration part is completed. Spring is not attached, so that's why I am not considering spring force. Now what about inertial force or movement? So since it is vibrating by rotation, so we will calculate inertial movement, and inertial movement will be I about I into angular acceleration. Angular displacement of rod is theta. So angular displacement of point mass is also theta, because it is attached the rod. So angular acceleration is theta double dot. So inertial moment will be I about I center into theta double dot, and direction will be opposite to theta double dot. Theta double dot is anti-clockwise, so it will be clockwise. Completed. Yes. So after that, in the body of this displaced position, we'll take summation of moment about I center and equate with 0. And while writing this equation, don't bother about the reaction which is coming at hinge, because moment of reaction at hinge about hinge will be 0. Yes. One by one. First of all, this inertial moment, it is already moment, so it will come as it is, I about I theta double dot. Direction, and sorry, clockwise, whatever first direction is coming, I am taking that positive. So this is movement is clockwise. For clockwise I am using plus sign, and for clockwise plus sign, then for anti-clockwise we'll use minus sign. Now movement due to this weight about I center, so it will be small mg. Now it is force, so whenever we are calculating movement due to force, it will be force into perpendicular distance. So now find the perpendicular distance of this force from I center, and this force is vertical now. So perpendicular distance means from horizontal distance. So horizontal distance of this point from I center is this distance. Now this is mathematics. You can see this angle is 90. After displacement, this length is L. This angle is theta. So in this triangle, this distance will be perpendicular, na? See, this L is in front of 90, so it is hypo. It is base. It is perpendicular. And perpendicular will always be hypo sine theta, because sine theta is perpendicular upon hypo. Suppose this distance is x1. So it is x1 upon hypo, which is L. So x1 will be L sine theta. So can I say here this distance is L sine theta? But again, for small oscillation, can I say sine theta will be theta, because theta is displacement in which is very less. So sine theta will be theta. So for a small oscillation, we can write this as L theta. Very simple. So perpendicular distance of this point force about from I center is L sine theta. For a small oscillation, it is will be equal to L theta. So perpendicular distance is L sine theta or L theta. Clear? Now what about direction? This weight is like this. You can see about I center it is rotating clockwise, and right now for clockwise I am using plus sign. That's why plus. No other effect is coming. So this will be equal to 0. I about I center is ml square theta double dot plus mgl theta equal to 0. We got the equation in general form. Coefficient of theta is ke or double dot is me, then omega will be root over ke me, or if some part is coming common, you can take common. Here m is coming. In both sides, one L is coming. Here L square is coming. Here L is coming. So ultimately, we can take ML common. Common part will come this side. It will become 0. And after taking ML common, here L theta double dot will remain. Here G theta will remain equal to 0. Here the coefficient of theta, which is G, will be Ke. So omega in root over Ke by M. Na? Ke is G. Okay. What about ME? M is the coefficient of double dot, which is M. So this is natural frequency of the system in radian per second. Even if you are taking this as K, this as ME, you will get same equation. Now, examiner is asking time period. Na? So, see, if omega when we have calculated, na, the time period of natural vibration or free undamped vibration is always 2 pi by omega n. So, 2 pi by omega n, and omega n is root over G by L. So, ultimately will become 2 pi root over L by Z. So, this is time period of this vibration, which is 2 pi root over L by G. 2 pi root over L by G, matching with which option? Option B. So for this question, the correct answer is B. I am discussing one more question as a numerical. This type of question can come exam. After that, I will discuss energy method. This is the last question in equilibrium method. Here you can see a rod of length L equal to 3 meters. So the length of this rod is 3 meters. I am taking in writing in diagram also. And mass capital M, the mass of this rod is capital M. I am writing separately, is 60 kg. Is hinged at top. Good, it is shown in figure. A point mass small m equal to 20 kg is attached at the bottom. So the mass of this point mass is small m, which is 20 kg. The rod is slightly rotated about top, that is about hinge, and then release. Then what will be natural frequency? Examiner asking in hertz. If you calculate in radian per second, you can calculate in hertz also. So what I am doing now, first I am locating the I center. See, both rod point mass is also attached at the rod. So ultimately, both are separate inertial body, but it will act as single system because point mass is also attached at the rod. And you can see this rod is hinged at this location. So can I say this is the I center of rod? Yes, because rod will rotate about this point. But since point mass is also attached at the rod, so point mass is also rotate about this point. So it is also the I center of point mass. Okay. So it is the I center of both rod and point mass. And here I will use equilibrium method in which I will use this equation after involving inertial force of moment, summation of moment about I center equal to 0. I will use this equation. So for that, first I am calculating I about I center for both rod and point mass. So first I am calculating for rod. Suppose for rod I am using suffix 1. So it will be I1. It will be. First locate the center of gravity of the rod. It will be at middle. Suppose this is G1. This distance is L by 2. Na? L by 2. L is 3 meters. So it will be 3 by 2. That is 1.5. Yes. So see. First calculate mass units of the rod about the center of gravity of the rod. And about center of gravity formula is ml square by 12. So it will be capital ml square by 12. But it is about center of gravity, that is about G1. Now to calculate about I center, we will use Paris theorem. For that, in this we will add a mass of the rod capital M into r dash square, where r dash is the distance of center of gravity, that is G1, and I center. Right now this distance is L by 2. So it will be L by 2 whole square. If you simplify this, it will come ml square by 3. But it doesn't necessarily you need to simplify this. Since it is numerical, so just put the value. Capital M is 60, L is 3 meter, L by 2 distance I already calculated 1.5 meter. Just put, you can calculate. Yes. Okay, but first I simplified, then I'm putting the value. But if you want, you can directly put the value also. See, capital M is the mass of the rod, which is 60 kg. L is the length, which is 3 meters. So 3 square divided by 3. So how much mass units of the rod about eye center is coming? 60 into 3 square divided by 3. You can check. It is coming 180 kg meter square. This is the unit of mass units. Now similarly, what will be the mass units of point mass about eye center that I am representing as I2? It will be, for point mass formula to calculate, I is mr square. So m is mass of this point mass, which is small m, into r square. R is the distance of this point mass and eye center, and this distance is equal to L, length of the rod. So it will be small m square. Small m is 20 kg, length is 3, so 3 square. How much it is coming? Again 180 kg meter square. So now we can calculate total I about I, means by combining the effect of inertia of rod and point mass. Okay. So total I about I. So it will be I about I of rod, which is 180, I about I of point mass, which is again 180. So it is 360 kg meter square. Now we can derive the equation of vibration. Now when you are deriving the equation of vibration, first conclude whether there will be role of gravity in restoration or not. Yes, there will be role of gravity, because whenever one vertical rod is hinged at any location and it is vibrating like this rotation, so there will be role of gravity, because due to weight there will be no static deflection in the spring. Here there is no spring. So if after rotating from its mean position, if it is coming back to the mean position, why it will come back? Due to the gravity. So here we will consider weight also in deriving the equation of vibration. Okay. So for that I am taking any position in which this rod has rotated by theta angle from its mean position. Theta is very small. Just for understanding, I am drawing a little bit bigger diagram. Okay. So this is theta. Right now I have taken theta anti-clockwise. So theta dot will also be anti-clockwise. Theta double dot is also anti-clockwise. Here point mass is attached, whose mass is small m. Now see, the center of gravity of the rod will be at the middle, na, G1, and this distance is L by 2. Value wise it is 1.5 meter. Now one by one. First of all, inertial moment. So mass units of both rod and point mass is I about I, which I have calculated, and angular displacement is theta. So angular acceleration will be theta double dot. So can I say here inertial moment will come, which is I about I theta double dot. Direction will be opposite to theta double dot. Theta double dot is anti-clockwise, so it will be clockwise. This is inertial moment, and it is the inertial moment of by combining the inertia of rod and point mass, because I about I is total inertia, mass inertia of the mass inertia about eye center for by combining the inertia of rod and point mass. Now since here restoration is occurring due to gravity, so we will consider weight, and here too we will consider the weight of point mass also and weight of rod also. Now see, the point mass is small m. So can I say weight of point mass will be small mg, and it will be at the center of gravity of point mass. This is the location of center of gravity of point mass. So here weight of point mass will come, which is small mg. If you want, you can wait for value also. Small m is 20 kg, g is 9.81. If g is not given, we will always take g equal to 9.81 meter per second square. Okay. Now weight of rod. So weight of rod will act at the center of gravity of rod, which is at this point. This distance is L by 2 or 1.5 meter, and mass of rod is capital M. So can I say weight will be capital mg? Yes. And it will again vertically downward. No other weight inner mass is given. So we have completed restoration part also. After that, what we'll do, we'll take summation of moment about eye center equal to 0. Summation of moment about eye center equal to 0. Now it will be, first of all, this inertial moment, it is already moment, so it will come as it is I about I theta double dot. It is clockwise. Whatever first direction of moment is coming, it is clockwise. I am taking that direction as positive. So I am taking clockwise positive. So anti-clockwise will be negative. It is I about I theta double dot. Tomorrow I will discuss 2 degree of freedom. Okay. I about I theta double dot. Yes. Now moment due to this weight about eye center. So this is small mg. It is force, and moment due to force will be force into perpendicular distance. So find its perpendicular distance from eye center. It is vertical. So you'll find its horizontal distance from eye center means this distance. Now this distance will be equal to, this entire distance is length of the rod L, which is 3 meter. Na? So can I say this distance will be 3 sine theta, but for a small oscillation, sine theta will be nearly theta, so it will be 3 theta. Okay. So moment due to the weight of point mass about eye center will be small mg. Its perpendicular distance from eye center, which is 3 theta. So it is small mg into 3 theta. Now what about direction? So how this force is rotating about eye center? This force is like this. This is eye center. So you can see about eye center, it is rotating clockwise. And for clockwise, I am using plus sign. So for anti-clockwise, we'll use minus. Okay. Now moment due to this weight about eye center, so it will be weight, which is capital Mg, into its perpendicular distance from eye center. It is vertical, so we'll find its horizontal distance from eye center means this distance. And what about this distance? See, this is 1.5 meter. This angle is theta, so it will be 1.5 sine theta. But again, for small oscillation, sine theta will be nearly theta, so it will be writing with different color. So it will be 1.5 theta. So the moment due to this weight capital Mg about eye center will be capital Mg into its perpendicular distance from eye, which is 1.5 theta. Now direction, this weight is like this, and about eye it is rotating clockwise, and for clockwise I am using plus sign, so that's why I used plus here. Okay. Now moment of reaction at eye about eye will be 0, so we don't bother about the reaction at eye. So this is completed, so it will be equal to 0. Now just put the value. I about I total is 360 kg meter square, so 360 theta double dot plus small m is 20 kg na, so 20, if g is not given, take 9.81, yes, into 3 into theta, but here also theta is coming, here also theta is coming, so I am taking theta part common, so it will be plus theta I am taking common, capital M, which is 60 kg, you can check, yes, into g, it is 9.81 into 1.5 into theta, theta part I have taken common, this is equal to 0. Now you can see again it is coming in general form, like 360 double theta double dot plus this part is plus 60, yes, this part is coming 1471.5 theta. Just check the calculation. If I am doing calculation error na, you can correct me. Yes. Now we'll refer coefficient of theta as Ke and double dot as Me. Then omega n will be, that is natural frequency in radian per second. It will be root over Ke, which is 1471.5 upon Me, which is 360. So how much it is coming? Root over 1471.5 divided by 360. Please check the calculation. Is it coming 2.022 radian per second? But don't be in a hurry. Examiner is not asking omega n. Examiner asking frequency in hertz, which I am denoting as Fn. So this is omega n, frequency in radian per second. Now if frequency in radian per second is omega n, then frequency in hertz, that is Fn, will be omega n by 2 pi. Okay. Now here omega n is 2.021 divided by 2 pi. So how much frequency in hertz will come? It is 2.0121 divided by 2 divided by pi. Is it coming 0.322 hertz? Please check the calculation. If I am doing calculation error, it is your part. Correct that. I think right now it's correct. 0.322 hertz. So examiner asking frequency in hertz, which is 0.322. Okay, so like this we can solve the problem. Okay, but this method was equilibrium method. Similarly, now you can solve the problem by energy method also. In some question you will find energy method is more easy. It might be possible it will take little bit more time. If it is taking little bit more time, means it is lengthy. But although it can be lengthy for some question, but it is easy to solve as compared to equilibrium method. Na? Reason is very simple. Here I am using energy method. What is energy method? That I will explain, don't worry. But since it is an energy, and energy doesn't have direction, it is not a vector quantity, it is a scalar quantity. So like in equilibrium method, na, I was bothering about the direction of inertial movement, direction of weight, direction of spring force, like this. Here we need not to bother about the direction because energy has no direction. Okay, only I have to write the expression of energy. But what is this method? See, I am explaining first by this linear system. Just for understanding that, I will apply for rotational system. Like if any system is vibrating like this, suppose during vibration the displacement of this point mass m from mean position is x, so its velocity will be x dot, acceleration will be x dot. But what I am trying to explain here, if displacement of mass is x, since spring is directly attached to the mass now, the displacement of spring from its mean position is also x. See, right now we are discussing free undamped vibration because we are calculating natural frequency na. In free undamped vibration, we know there will be no loss of energy because there is no damping. And if there is no loss of energy, can I say here total energy will be constant? When I am writing TE, T is representing total energy. Total energy means it is the sum of kinetic energy plus potential energy, and it is constant. Okay. Now we know the differentiation of any constant is always zero. So what I will do now? I will differentiate this total energy expression. What I will do for this displaced position, I will find the expression of total energy, and I will differentiate total energy with respect to time. And can I say in free undamped vibration, in free undamped means there is no damping, undamped vibration, the differentiation of total energy with respect to time will be zero. Reason, total energy is constant and differentiation of constant is zero. And total energy is nothing but mainly the summation of kinetic energy plus potential energy. So what I need to do now, for displaced position, we'll find the expression of kinetic energy, potential energy, add them, that will be total energy, differentiate with respect to time, equate with zero. Automatically you will get the equation of vibration. Very simple. Very simple. This is energy method. Okay. But this equation is only valid, this method is only valid for free undamped vibration, because total energy will be constant when there is no damping. Okay. Now, how we can find kinetic energy and potential energy? For this question, I am explaining. See, kinetic energy will come due to inertia, because formula to calculate kinetic energy, if any body is translating now, any mass is translating, then we know the formula to calculate kinetic energy is half mv square, where m is the mass of that body, v is the linear velocity of that body. Okay. Similarly, if any mass is rotating, then how to calculate kinetic energy, that I will explain. But right now, first I am explaining this method for translating system, na? Just for understanding. So see, the here in this mass is having inertia. Mass of this the mass of this body is small a, and it is translating. So I will use half mv square formula to calculate kinetic energy. For that, see its velocity. So displacement of mass from its mean position is x. So velocity will be x dot. That's it. Direction is not important. Only velocity value. It is x dot. So can I say kinetic energy will be half mx dot square? Completed. Right now spring is massless, na? And kinetic energy will come due to that body whose mass or inertia is there. So I am half mx dot square. Now what about potential energy? See, here student might get confused, but I am explaining. See, whenever there is no role of gravity in the restoration. Okay. And right now in this question, there is no role of gravity in the restoration. First see this. So like during equilibrium method, when there was no role of gravity in the restoration, and why there is no role of gravity in the restoration? Because due to weight, static deflection will come in the spring and they will cancel each other effect. Means there is no role of gravity in the restoration. Okay. And if there is no role of gravity in the restoration, like in equilibrium method, we were not considering weight. Similarly, we were not considering static deflection part also. Similarly, if there is no role of gravity in the restoration, while calculating potential energy, neither will consider weight. Weight means, because if we are considering weight, now here you can see datum is changing during vibration. If any mass is moving up and down, then datum is changing. And datum is changing, then formula to calculate potential energy you have studied in mechanics is mgz. But what I am saying, if restoration is not occurring due to gravity while deriving equation of vibration, neither will consider weight, nor we will consider static deflection part of the spring. Okay, so since I am not considering weight, I will not take mgz. Similarly, when you are calculating potential energy due to spring, don't focus on the static deflection of the spring, that is delta. Focus on the deflection of spring from mean position. Okay, it is little bit complicated, but try to understand. I am not going on detailed derivation. Okay, what I am saying, if there is no role of gravity in restoration, just think in simple. Don't consider weight and static deflection. That's it. Okay. So here I will only calculate potential energy due to spring, And due to this displacement is displacement from mean position. And I think you have studied in mechanics in 11th, 12th also. Formula to calculate potential energy due to spring is half kx square, where k is the stiffness of spring, if it is linear spring, and x is the displacement of spring from mean position. Right now, the stiffness of this spring is k, and see the displacement of spring from mean position, not total displacement, it is x. So it will be half kx square. Means potential energy will come due to that part which is responsible for restoration. So half kx square. Now don't think, sir, here x, this datum of mass is changing, so mgx will come. It is coming going below, so with minus sign it will come. No, here I am not considering datum energy. Reason? Because here no role of gravity in the restoration. If you will calculate datum energy na, then you have to calculate the static deflection of the spring at mean position also. Okay, and if you are considering this two part na, after derivation finally you will get this relation. But that derivation is not at all important. Just think, first of all, potential energy, formula to calculate potential due to spring is very simple, half kx square, where x is displacement from mean position. After that thing, we should take datum energy or not. Very simple. If there is no role of gravity in the restoration, we will not take datum energy. Okay. How it is getting eliminated, don't bother about that. Just if there is no role of gravity in restoration, I will not take datum energy. Okay. And if there is role of gravity in restoration, in this question there is no role. But if in some other question if there is role of gravity in the restoration, it means weight will not cancel with static deflection. In that case, we will consider datum energy. But right now here weight will get cancelled with static deflection, means already concluded there is no role of gravity in the restoration. So when calculating potentials, don't consider datum energy part. It will get cancelled with static deflection energy part, but how it is cancelling, don't bother about that. Very simple. No role of gravity, so only consider potential energy due to stiffness of spring, which is k, is displacement from mean position is x, so it will be half kx square. Since there is no role of gravity in restoration, I will not consider datum part. That's it. After that, we'll calculate d by dt of total energy, and total energy is kinetic energy, which is half mx dot square plus potential energy, which is half kx square, and equate with 0. Now half m differentiation of x dot square with time. So first of all, I am using chain rule. First differentiate x dot square with respect to x dot, so it will be 2x dot. Now we'll differentiate x dot with respect to time, and differentiation of x dot with respect to time is x double dot. Similarly, plus half k x square. Now differentiation of x square with respect to x will be 2x. Now differentiation of x with respect to time is x dot, that is equal to 0. Now you can see half is coming common, that will come this side, it will become 0. 2x dot is coming common, it will come this side, it will become 0. And apart from this, here mx double dot is remaining, plus here kx is remaining, equal to 0. Now this equation is same is like this, which we had derived by equilibrium method. Same equation we are getting. Yes, same equation. Yes. But for general case, we have remembered, just for understanding, I explain this method. Na? Okay. And omega n will be root k by n. Okay. Means the method is, for displaced position, we will calculate kinetic energy, potential energy, add them, that will be total energy, differentiate with respect to time, equate with 0. Now, when mass is rotating, then how will calculate these things? Okay. Best part of energy method is, here we need not to bother about direction, because energy has no direction. Now, see, if you are calculating kinetic energy, now first I am explaining kinetic energy part. Okay. So for the body whose inertia is given, calculate kinetic energy. If that body is translating now, suppose this mass is m, it is translating, its displacement is x, so velocity will be x dot, acceleration will be x double dot. So formula to calculate kinetic energy is half mx dot square. Okay. X dot is the velocity, na? Yes. But if it is rotating or rotating plus translating, very simple. It is rotating body or rotating plus translating body. In that case, na, only you have to find the I center of that body. Okay. And what we'll do, we'll calculate I about I center. What is I about I center? I have already explained. It is mass inertia about I center, and we'll calculate its angular velocity. So suppose angular displacement is theta, so angular velocity will be theta dot, acceleration will be theta double dot. So see angular velocity. So see, formula to calculate kinetic energy in case of rotation motion is na, instead of mass moment inertia about I center will come. So it will be half instead of m I about I center, and it is mass moment inertia not about any point, it is about I center, into instead of angular velocity will come. Now if angular displacement is theta, angular velocity will be theta dot, so theta dot square will come, and both are energy na, so both will be in joule. If in any vibratory system there is translating mass also, rotating mass also, so for translating mass use this formula, for rotating mass use this formula, add them, you will get total kinetic energy. So like this you can calculate kinetic energy. Now potential energy if potential energy due to spring is coming now, that I have already explained. If the spring is linear spring now, just see the stiffness of spring is k and displacement of this spring from mean position, if it is x, potential energy will be half kx square. If it is x1, it will be half kx square. Similarly, if it is torsional spring whose stiffness is kt, then see its angular displacement. Suppose angular displacement from mean position is theta, so potential energy will be half, instead of kt will come, which is stiffness of this torsional spring, and instead of linear displacement, angular displacement will come, so half kt theta square. But both are in energy na, so both will be in joule, so just add them because both are energy. Now in potential energy we'll consider mgz or not. So if there is no role of gravity in restoration, if due to weight static deflection is coming in the spring, so there will be no role of gravity in the spring. In that case, we'll never consider mgz datum, that is datum energy part, while deriving the equation of vibration. If there is no role of gravity in the restoration, if there is role of gravity in the restoration, then we will consider mgz part. Okay, but right now I am discussing those questions in which there is no role of gravity in the restoration. Okay, so this is all about energy method. Na? I will explain with one question, so it will be better clear. And I am taking the same question which I had taken as reference when I was explaining equilibrium method for rotating board, rotational vibration, just to ensure that answer in both method is coming same. Now see, first of all, this rod is hinged, so this will be I center of the rod. Now this point mass is also attached at the rod, so this is also the I center of point mass. Now first of all calculate total I about I, because I center of both rod and point mass are same. But this calculation I have already done na, so same thing will repeat. So you will calculate mass energy of rod about I center, it will come capital ml square by 3, because this calculation I have already done. You calculate mass energy of point mass about I center, it will be small ml square. Now what I am doing, take any position during vibration in which this rod has rotated by theta angle from its mean position, and right now I have taken theta clockwise, and now angular displacement is theta, so velocity will be theta double dot theta dot, and angular acceleration will be theta double dot for this rod. Yes. Now what about gravity? There is role of gravity in restoration or not? No, because the weight of the system is supported by spring, so in mean position due to weight there will be static deflection in spring, and they will cancel each other, their effect. So there is no role of gravity in restoration. Okay. So when you calculate potential energy, only calculate due to stiffness of the spring, and in that formula don't take total displacement, take the displacement spring from mean position. Okay, we will not consider datum energy. So for total energy, first I am calculating kinetic energy. It is very simple. Right now both rod and point mass is having rotating about I center, so we'll use this formula, half I about I into angular velocity square. So half I about I, and total I about I in this case is capital ml square by 3 plus small ml square, into, if angular displacement of rod and point mass is theta, so angular velocity will be theta dot, so it is theta dot square. So this is total kinetic energy na, because I had taken the inertia of rod also, inertia of point mass also. That's it. Now in potential energy we will take that part due to which restoration is occurring. So due to this linear spring, first of all, for that the displacement of linear spring from mean position, suppose this displacement is x1. Now we can write x1 in terms of theta na, x1. Distance of this point from I center is a, so x1 for small oscillation is x1 will be a theta. So one by one. Potential energy due to this torsion spring, formula is half kt theta square. So kt is the stiffness of this spring, and theta is angular displacement of spring. So angular displacement rod is theta, so angular displacement spring from mean position is also theta. So can I say potential energy due to stiffness of this torsion spring will be half kt theta square. Now what about due to this linear spring? Half, and it is energy, so always use plus. It is potential energy. So that's this is also potential energy, and due to linear spring also potential energy will come, and energy unit is always joule, na? So just add them. So stiffness of linear spring is K. Now displacement of linear spring from mean position is x1, so it will be K x1 square. That's it. Now datum part will take or not? No, because since there is no role of gravity in restoration, so we will not consider datum part. It will cancel with static deflection part, but how it is cancelling, don't bother about that. So this is total potential energy. Now x1 is a theta, so I am doing this replacement. Half you can take common. It is kt theta square. Kt I am taking common. Now see, x1 is a theta, so it will become a theta whole square means a square theta square. So ultimately it will be k a square theta square. Half I already taken common. K a square theta square. Here also theta square is coming. So I am taking theta square also common. So it will be kt plus k square into theta square. So this is total potential energy part. After that, very simple. In energy method, d by dt of total energy is 0. Total energy means kinetic energy, which is half in bracket capital ml square by 3 plus small ml square theta dot square plus potential energy, which is half in bracket kt plus k square theta square equal to 0. Just do the differentiation. Half in bracket capital ml square by 3 plus small ml square. Now differentiation of theta dot square with time. First differentiate theta dot square with respect to theta dot. So it will be twice of theta dot. Now differentiation of theta dot with respect to time, it will be theta double dot. Yes. Plus half in bracket kt plus k square theta square differentiation. Now theta square differentiation with respect to theta is 2 theta. Now differentiation of theta with respect to time is theta dot, that is equal to 0. Now half I am taking common, that will come this side, it will become 0. 2 theta dot, and here also 2 and theta dot is coming, so it will also come common, it will come this side, it will become 0. So apart from common part, here I am capital ml square by 3 plus small ml square theta double dot is coming plus kt plus k square theta is coming equal to 0. It is in general form. Now coefficient of theta is k, which is kt plus k square upon coefficient of theta double dot is ma, which is capital ml square by 3 plus small. Okay. So this is the natural frequency of the system in radian per second. Same answer we got by equilibrium method also. Just I am discussing one more question. In this question I am discussing by energy method. See, the system shown in figure consists of block A. Actually it is typing error, it is A, na, of mass 5 kg. Suppose the mass of the block is m, which is 5 kg, connected to a spring through a massless rope. This rope is massless, passing over a pulley P, this pulley is B, of radius r and mass 20 kg. The mass of the pulley, suppose that I am representing, suppose mass of this point mass I am representing as ma, mass of pulley I am representing as mb, so it is 20 kg. Yes, radius is r. Stiffness of the spring is K, which is 1500 Newton per meter. Then we have to calculate natural frequency of the system in radian per second. Okay, and this rod is this pulley is hinged at the center. Now how we can calculate? Now use I will suggest in numerical use always SI unit time. Okay, and I am using energy method. Now see, see, suppose this I am talking about this pulley. Pulley is hinged at center. So can I say this is the eye center of pulley? This is the eye center of pulley. Okay, good. Now suppose I am taking any position in which this pulley is rotating by theta angle from its mean position during vibration. I am taking the position. Now see, if this pulley has rotated by theta angle and I am taking theta clockwise, it is your will. If you want to take clockwise, take clockwise. If you want to take anti-clockwise, take anti-clockwise. Right now I have taken theta as clockwise. So angular velocity will be theta dot, angular acceleration will be theta double dot. Good. Yes. So see, if it is rotating theta clockwise, so can I say this point will move in this direction like this? Suppose this displacement is x1, and x1 you can write in terms of theta. And if this point is displacing by x1 amount, So can I say this spring will also displace by x1 amount? Yes, from mean position. This is the displacement from mean position. And x1 in terms of theta I am writing here. See, the distance of this point from I center is r, which is equal to radius. So x1 will be equal to r theta. Similarly, if this mass will translate na. So if I want to find the displacement of mass, for that find the displacement of this point. If it is rotating clockwise, it will go downward like this. And suppose displacement of this point is x2. Okay. So x2 expression also you can write in terms of theta. Distance of this point from I center is again r. So here x2 is also r theta. Yes. And if the displacement of this point is x2, the displacement of this point mass will also be x2. Here this pulley is rotating about this point, but here this point mass is having translation motion. So if we are calculating mass kinetic energy due to pulley, use half I about I omega square. Omega is angular velocity, and we are calculating kinetic energy due to this point mass, use half mv square, where v is the linear velocity of the mass because it is translating na. And x1 is r theta, x2 is also r theta. Yes. Clear? Yes. Now what we'll do, we'll calculate kinetic energy and potential energy part. First of all, calculate kinetic energy. It is very simple. Kinetic energy will come due to that part whose inertia or mass is given. So inertia and mass is given for pulley and this point mass. Now for pulley, I will use half I about I omega square formula to calculate kinetic energy, where I about I is mass inertia about I center and omega is angular velocity of the pulley. Okay. So first calculate mass inertia of this pulley about I center. Okay. Now in this question right now, no expression is given to calculate the mass inertia of pulley about I center. If no expression is given now, so you'll always consider the shape of the pulley as a disc, as a solid disc. Okay, solid disc. And formula to calculate, I am writing separately. This formula you should know, na. For the solid disc, if it is the like a shape of solid disc, for solid disc, suppose the mass of this disc is m and radius is r. This is center of gravity, which will be at center. For solid disc, formula to calculate mass about the center of gravity is mr square by 2. You can remember this formula. And if we want to calculate about any other point, you can use Palik's theorem. So right now we have to calculate mass inertia of this pulley about I center. And right now you can see the I center of pulley is lying at the center of gravity. So whatever is the formula to calculate mass inertia of pulley about center of gravity, that will be the formula of mass inertia about I center also, because it is coinciding with center of gravity. And the formula is mr square by 2. M is the mass of this pulley, which is mb, into r square divided by 2. R is not given, na, value of r is not given, so keep right like as r. But mass of pulley B is given, it is 20 into r square by 2, so it will be 10 r square. So see, kinetic energy due to inertia of pulley will be half I about I of pulley. I am writing directly, na, which is 10 r square into omega square. Omega is angular velocity. So angular displacement of pulley is theta. So angular velocity will be theta dot. So it is theta dot square. Or always write with plus n because it is energy. Energy has no direction. Now kinetic energy due to this. So formula will be half mv square because it is having linear motion. So mass of this point mass is 5 kg. So kinetic energy due to this half in bracket. Why I am directly adding? Because both are energy. Both will be in joule. 5 into v means linear velocity. So see, the displacement of this point mass is x2. So can I say its linear velocity will be x2 dot? And you can write the expression of x2 dot in terms of theta dot also. How? See, we know x2 in terms of theta, it is r theta. So if you differentiate this with respect to time, you will get the expression of x2 dot. So differentiation of x2 with respect to time is x2 dot, r is constant, and the differentiation of theta with respect to time is theta dot. So your x2 dot is nothing but r theta dot. So see, first of all, formula half mv square, and velocity of linear velocity of this point mass is x2 dot. So into x2 dot square. No other inertia is given, so this is complete. Just simplifying this, half I am taking common. It is 10 r square theta dot square plus 5. Now x2 dot is r theta dot. So ultimately after putting, it will be r theta dot whole square, which is nothing but r square theta dot square. So ultimately half I am taking common. It is r square theta dot square. It is also r square theta dot square. So r square theta dot square I can take common. So here 10 will remain, here 5 will remain. And 10 plus 5 is 15. So it will be 15 r square theta dot square. That is the expression of kinetic energy. If you want to write 15 divided by 2 as 7.5, you can write, it is your will. Okay, I am just writing like this. This is kinetic energy. Now what about potential energy? So here potential energy will come due to stiffness only, because there is no role of gravity in the restoration, because due to weight static. See, although the datum of this mass is changing, but due to the weight of the system, na, static deflection will come in the spring, because weight of this mass is supported by spring. So they will cancel each other effect. So that's why I am not considering datum or potential energy while writing the datum potential energy due to datum part while writing the expression of potential energy. It doesn't mean I am neglecting that. It is getting cancelled with static deflection part, but how it is cancelling, we need not to bother about that. So here, since there is no role of gravity in restoration, while writing the expression of potential energy, I will only write potential energy due to stiffness of the spring. And here one spring is attached whose stiffness is K, and displacement of this spring from mean position is x1. So potential energy will be half kx1 square. That's it. Now half K is given, it is 1500 Newton per meter. X1 is r theta. So it will be r theta whole square, means ultimately it will be r square theta square. R square theta square. Clear? Yes. And after this, I can write total energy. And differentiation of total energy with respect to time is 0. So d by dt of kinetic energy, which is half in bracket 15 r square theta dot square plus potential energy, which is half in bracket 1500 r square theta square equal to 0. Now half into 15 r square, differentiation of theta dot square with respect to time. So first of all, differentiation of theta dot with respect to theta dot is 2 theta dot. Now differentiation of theta dot with respect to time is theta double dot plus half 1500 r square. Differentiation of theta square with respect to theta is 2 theta. Now differentiation of theta with respect to time is theta dot equal to 0. So see, half will come common, it will come this side, it will become 0. Common part I am doing underline. Na? Similarly, this 2 theta dot, this 2 and theta dot will also come common, it will come that side, it will become 0. And apart from this, similarly you can take r square also common. Here also r square is coming, here also r square, and r square will come that side, it will become 0. So apart from this, here 15 theta double dot will remain. Here I think 1500 theta will remain. It is in general form, equal to 0. Now coefficient of theta is Ke, which is root over omega n will be root over Ke by me, where K is coefficient of theta, which is 1500, upon m is coefficient of theta double dot, which is 15. So from this I can calculate omega n, which is natural frequency of the system in radian per second. How much it is coming? Root over 1500 divided by 15, it is coming 10 radian per second. Clear? So natural frequency of the system in radian per second is 10 radian per second. Exam asking radian per second. So correct answer for this question is 10. So like this you can solve. Similarly in class we will discuss various questions, na? But through this some examples I had tried to explain the equilibrium method and energy method to derive the equation of vibration, and after that finding natural frequency. Okay. Now whenever any new question is coming in the exam, you have to first think for that question, just go in your gut feeling. As per you, which method will be easy? Equilibrium method or energy method? If you are thinking that equilibrium method is easy, you will not face in difficulty in drawing the direction of inertial forces or movement or restoring forces and movement, then use equilibrium method. Otherwise, if you are getting confused in directions, use energy method. Okay. But one limitation of energy method is not valid in damped vibration, but equilibrium method is also valid in damped vibration. Only difference is in damped vibration, damping force or movement will also come into picture, but that will discuss when we will discuss damped vibration. In today's class, my objective was only to discuss the free undamped vibration of rotational system. Okay. Tomorrow I will take the class in which I will discuss for spring mass system how to calculate natural frequency, but for 2 degree of freedom system. Tomorrow I will discuss how to calculate natural frequency of 2 degree of freedom system. But that's all for today class. I think it is clear to everyone. Okay. So we'll meet in some other classes with some other topic. Tomorrow we'll discuss vibration of 2 degree of freedom system. Okay,